Okay, so now we're looking at the example of locating or figuring out Quinn's percentile. Remember last time what we had to do was set up this normal curve, which while all the percentages were the same, we had to relabel the x-axis depending on our data set. So every single time, be it machine 1, machine 2, or this SAT example, though the percentages stayed the same, we had to go through the trouble of labeling the x-axis. Then we located our data value. In this case, our data value was 697, which put us here. We decided whether we wanted to be above or below. For percentiles, it's always below. And then we added up all of this, all the percentages that I have shaded in blue. We no longer need to go through that whole process. Remember, we're only going to be working off of this one curve. So whether we have machine 1 with its mean and standard deviation, or whether we have machine 2 and it had a different mean and standard deviation, or now we're dealing with the SATs, it doesn't matter. As long as we find our z-score, we can plot ourselves on this normal curve and then answer the question at hand. So we're going to go ahead and find the z-score. Remember, to find a z-score, we start out with the data value, and then we will subtract off the mean and divide by the standard deviation. So z is calculated by x minus x bar divided by s. In this case, our data value in question was Quinn's score of 697. We subtract off the mean of 518 and we divide by 115. This gives us a z-score of 1.56. Okay, well, what does that mean? It means that we're more than one standard deviation away from the mean, but not quite 2. And because it's positive, that puts us to the right, which makes sense because Quinn's score of 697 is higher than the mean of 518. So we should be to the right of the mean. All right, so again, we are more than one standard deviation away, but not quite 2. And 1.56 is just about smack in the middle, which is what we determined when we specifically plotted that 697. All right, percentile implies we want the percent of data below, so that's all of this. And so here again, we can see we would add the 2.35, the 13.5, the 34, the 34. We do run into the situation where we have to estimate this piece that I'm darkening, okay? Remember, even though we're about halfway between 1 and 2 standard deviations, everything that I've darkened in blue is that whole area is larger than this. So just cutting that 13.5 in half and calling it 6.75 is not going to be a good enough approximation. We'd have to bump it up. So if we bump it up to 10 like we did before, that gives us our approximately 94th percentile. All right, so in the last 3 videos, this one and the shortcut for machine 1 and machine 2, you see how we no longer have to create a different normal curve for every data set that we have. We can just work off of this general normal curve. The problem is, though this has shortcutted that whole process, what we have not avoided is this estimating. In class, we're going to talk about how we can get more accurate answers by using something called a z-table. So in class, I will introduce you to that. So as of right now, we've been able to shortcut this whole process, but we have not been able to avoid estimating. Due to the need for accuracy, we will discuss how we can be more accurate in class.